So for my number 6, my function is the following. It's x minus y times 4 minus xy. What you have too? I'm like, well, maybe I'm going to change it then. No, fine. Okay, so, all right. So what are they asking us to do? They're asking us to find the local maxima of f, the local minima of f, and solve it. So let's see. So each answer should be a list of points A, B, C separated by commas. There are no points, the answer should be none. So we're trying to find the x, y, and z coordinate of our local maxima, local minima, saddle points. So got to find the partials. You can kind of go one of two ways here. You could multiply this whole thing out, or you could use the product rule. I'm kind of indifferent. Let's see what using the product rule looks like. So we take the partial with respect to x. It's going to be the derivative of this piece, which is 1, times the other piece, which is 4 minus xy, plus this piece, which is x minus y, times the derivative of this piece with respect to x, which is going to be what? What's the derivative of that piece with respect to x? Negative y. So this doesn't seem particularly useful to do it this way. I'm thinking it probably would have been better if we had multiplied this out first and said this is really going to be 4x minus x squared y, and then minus 4y plus xy squared. And so if we take the partial of that with respect to x, I mean, you're going to get the same answer, just going to be multiplied out. Our partial would be the derivative for x would be 4, the derivative of x squared y would be minus 2xy, derivative of 4y is 0, and the derivative of xy squared is y squared. And we can see that if we multiply this out, we would get 4 minus xy minus another xy, which gives you the minus 2xy, and a plus y squared, which gives you that. So same either way. Let's look at the other partial. So we've got fy, and let's just look at this one. So taking the partial with respect to y, we're going to get a negative x squared, a negative 4, and a plus 2xy. So I see why you are curious about this one, because this looks challenging to solve for the critical points, right? Like I'm not actually sure how I'm going to go about finding the critical points here. So neither of these look particularly easy to solve for x or y. Like you don't just get like unlike the examples I've given us, we don't have a y or an x factoring out nicely. So when that kind of fails, we should do another problem too, but when that fails, we're gonna solve for what we can. So I'm gonna look at this equation and try solving for y. So I'm gonna have 2xy equal to x squared plus 4, and then dividing both sides by 2x, y equal to x squared plus 4 divided by 2x. And then I'm going to substitute that in for y over here, which might be a giant mess, right? This might not work well. We're going to find out. So then this equation, I have 4 minus 2x times y, which is x squared plus 4 over 2x, plus y squared, which is x squared plus 4 over 2x squared. Okay, that looks not lovely, but oh well, such is life. One thing that is nice here is the 2x's cancel for this first part. So I really got 4 minus the whole quantity x squared plus 4. Be careful, it's easy to lose the parentheses there and forget to distribute the minus sign. Here, not thrilled. So squaring the top out, I've got x to the 4th plus 8x squared plus 16. Squaring the bottom out, I've got 4x squared. That does not look great. I would probably multiply everything by the denominator just to get rid of the denominator. If I multiply everything by 4x squared, I'm going to have a 16x squared, a minus 4x squared times x squared plus 4, and a plus x to the 4th plus 8x squared plus 16 equal to 0. Okay, so then 16x squared minus 4x to the 4th minus 16x squared plus x to the 4th plus 8x squared plus 16 equals 0. Start canceling things. So I've got a negative 3x to the fourth plus 8x squared plus 16 equal to 0. Man, this does not look good. Really does not look good. Let's see. I would get rid of the negative sign. So here's what I'm seeing at this point. This might factor like a quadratic. I would probably get rid of the 3 or the negative and say it's 3x to the fourth minus 8x squared minus 16 equal to 0. So one potential guess is this could factor as something like 3x squared and an x squared. I don't actually know if this is going to work though. Oh, there's a way of doing this that I'm terrible at. You do A times C and then you look for things, right? You guys, are you familiar with that? What's that? Slide. I've never heard that. I like it though. So I know that 3 times negative 16 is negative 48. And you're looking for things that multiply to negative 48 and add up to negative 8. And that, yeah, 4 and 12, negative 8 and positive 12. Positive 12, positive 4. Positive 4, no, sorry. Negative 12 and positive 4. Now, this doesn't factor as 3x squared minus 12 and x squared plus 4. You have to do this thing where, yeah, fine. I got ahead of myself over here. So I've got 3x to the fourth minus 12x squared plus 4x squared minus 16 equal to 0. That's the way I've always done it. There's lots of ways of doing this. Like whatever method of factoring works for you, great, use your method. I'm just showing you what works for me, which is where I write the negative 8x squared as the negative 12 plus the 4, and then I factor this part by grouping. So I'm going to have a 3x squared I can factor out from this first thing, and I'm left with an x squared minus 4. And from the second thing, I can factor out a 4, and I'm left with an x squared minus 4. And then finally, when I factor that by grouping, I get a 3x squared plus 4 times an x squared minus 4. So after all that, if we factor one more step, 3x squared plus 4 equal to 0 is not going to give us anything. 3x squared is always non-negative. Add 4, it's always bigger than or equal to 4. So this part doesn't help us at all. But if we rewrite this whole thing as 3x squared plus 4 times x minus 2 times x plus 2, we get x equal to 2 or x equal to negative 2. Wow, it's a lot. We're not done yet, you too, right? It's a lot, we're not even done. But we can then go back and see, okay, great. If x equals 2, then y is going to equal 2 squared plus 4. So 4 plus 4 over 2 times 2, which is 4. So y is going to equal 2. And if x equals negative 2, we're going to get 2 squared plus 4. So again, 4 plus 4, but this time over negative 4. So we're going to get negative 2. And my best guess is that these are the only critical points. Now, I should mention, it is possible that if we had started over here, to be thorough or exhaustive, we should probably, I'm not gonna, but we should probably check to see if you actually start off by solving for x here first. If you do 2xy equals 4 plus y squared and then divide both sides by 2y. If you solve that for x and then plug it into the other one, if you get something else, just something to think about checking. I'm not going to do that, but you can, or you might need to if what we find here isn't sufficient. All right, so then we've got our critical points. And let me just write down fx and fy again. So fx is 4 minus 2y plus, 2yx plus y squared. And fy is, where'd you go? Negative x squared minus 4 plus 2xy. So then putting those things together, or sorry, not putting them together, critical points, 2, 2, and negative 2, negative 2. So then to see if it's a max or minor saddle point, we do the usual thing. We find gamma. So fxx is going to be negative 2y. Fyy is going to be what? Yeah, 2x. And fxy is going to be, I don't think so. Negative 2x plus 2y, I believe. Sure. Oh, I see. Yeah. So then our gamma of x comma y is that times that. So negative 2y times 2x minus negative 2x plus 2y squared. And then we'll plug in each one. So if we plug in 2, we're going to get negative 4 times 4 minus negative 4 plus 4 is 0 squared. So when we plug in 2, what do we get? Max, min, saddle? Saddle, right? Less than 0. So we have a saddle here. And I think we're going to get the same result if we plug in negative 2, negative 2. Because we plug in negative 2, negative 2, negative 2 times 2 is 4. 2 times negative 2 is negative 4. And then if we plug in negative 2 and negative 2 for each of these, you get 4 plus negative 4, which is again 0, which is again negative. So it looks like we have a saddle there as well. And then to fully answer the question, we have to go back and say, okay, well, if we plug in 2 to the original function, f of 2 is 2 minus 2 times 4 minus 4, which is 0. And f of negative 2 is also going to be 0 because it's negative 2 minus negative 2 times 4 minus 4 again, which is 0. Interesting. Something else I want to say here. So if these are our only answers, our answers are going to be 2, 2, 0, and negative 2, negative 2, 0. Now, instead of doing all the other work, not that I'm saying there is other work to do necessarily, but what I might do at this point, or might have done to start off, is actually graph the thing to see what it looks like, just so I have an idea of how many answers I'm really looking for. So let's see, graphing. Let me just type it in here where it's easier for me to see things. I'm just going to plug. I feel like I remember seeing. I think I remember seeing like a question like this a few quarters ago, and I think a student and I got really stuck because we missed the part that you had to put all 3 coordinates, and we were only putting the 2. We just couldn't get the right answer. But I'm pretty sure it's this. Let's see. So we've got z equal to, where'd you go? Function x minus y times 4 minus xy. Ooh, that looks bonkers. Ooh, I don't know if we found all the things. Oh, shoot, come on. So that looks, so I see a saddle there. No, I think maybe we might have found all the things. There might just be 2 saddles. You see the saddle there? And then there's a saddle over here. I'm sorry. And it looks like those are occurring at 2, 2, 0 and negative 2, negative 2, 0. And what's going on with 0, 0? That looks bonkers. Oh, anyway, this seems, at least to me, like enough evidence to feel comfortable with my answer. If that doesn't turn out to be all of the answers, I would highly recommend doing what I said as far as taking, instead of starting with fx equal to 0 and solving for y. Oh, sorry, you can't see what I'm pointing at. Instead of starting with fx equal to 0 and solving for, we did that over here, we solve for y as a function of x, and we plug that into the other equation over here. In fact, let me draw a little arrow so I can be like, ooh, this went in right there. I would, if this doesn't turn out to be all the answers, then we should start with setting this equal to 0, solving for x, and then plugging that into the other one to see if we get other critical points. My gut is telling me that there aren't other critical points, but that doesn't mean I'm right. Okay, that's a challenge. That's a challenging question for sure. It definitely is hard. So this is kind of, in my opinion, the hardest situation where you don't just get a nice X or Y value coming from one of the partials equal to 0. And so then you have to plug like a function of one variable into the other thing. I could give you another example of that if you're interested, but we don't have to if you're not. You can say like, no, yes, something. Are there other homework questions that are troubling? This is due on Friday, right? Yeah.
I have some questions like, just like,
Sure. Sure. Sometimes numbers get big. It certainly looks like you've got the right idea, but it's probably worth, I don't mind looking at one like this again, because I think it's worth our time to kind of just make sure we go with the process. Also, I feel like some of the examples I did on Monday were not, they were not excellent. They were fine, but they could have been better. So let's look at something like 12, because I think it's worthwhile. So find the minimum and maximum values of this function. I guess I could label this one as number 6. Right, it was number 6. Yeah. So the number 12 I have is find the minimum and maximum values. So specifically, they're only asking for the output of f of x, y, z equal to 3x plus 2y plus 4z, subject to the constraint x squared plus 2y squared plus 6z squared. I'm just going to write it as -1 equal to 0. And that's our g of x, y, z. It's just, I always think it's worth pointing out, right, that this thing on its own, like, doesn't have a max or a min. This function of x, y, and z, if you're thinking about, like, well, I guess it's kind of, I mean, really, it's hard to think of this as a surface unless you set it equal to a constant. But if you did set it equal to a constant, whatever constant you set it equal to, this would just be a plane. So if you think about a plane, like kind of sitting, you know, like this or whatever, it doesn't have a maximum or a minimum, right? It just keeps getting bigger and bigger and bigger and smaller and smaller and smaller, right? But it doesn't ever top out unless you restrict its domain to some region so that you get something. Kind of like that example we saw last class where I did the graph of it, and it was like it was the surface, and then we cut it with a cylinder, and we saw that, oh yeah, there's the maximum there, and there's a minimum there. Like that, I think that was a good example of how, like, this thing on its own doesn't actually have a max or a min, but if you cut it with something else, then on that thing you're cutting it with, then you get maxes or mins. So this definitely, to me, looks like a LaGrange multiplier type of question. It doesn't actually say to do one or the other, but I don't really want to solve this equation for one of my variables and plug it into that equation and try to maximize it. It doesn't seem smart. It probably would work, but when you're having to square root something to plug into the other thing, it just seems like it's probably a good indication that we should go the other direction. So let's use Lagrange. So our capital F of x, y, z, lambda is lowercase f minus lambda times g, which is just a big mess to write. 3x plus 2y plus 4z minus lambda times x squared plus 2y squared plus 6z squared minus 1. Oh, not equal to 0. Don't be silly. And then we're going to take all the partials. So fx is going to equal 3 minus lambda times 2x. Set that equal to 0. Fy is going to equal 2 minus lambda times 4y. Set that equal to 0. And fz is going to equal 4 minus lambda times 12z. Set that equal to 0. And I think this is the situation where we do what I typically do, where we just solve each of these for lambda. So solving this first one for lambda, we're gonna get lambda equal to 3 divided by 2x. Solving this one for lambda, we're gonna get lambda equal to 2 divided by 4y, which I should reduce to 1 over 2y. And solving this one for lambda, we're gonna get 4 divided by 12z, which is 1 over 3z. Is that how he has been doing in class, or does he do something else? Okay, what does he do?
Like he numbers.
Oh, which will cancel out the lambdas. Well, yeah, kind of. Yeah, weird. Weird. Let me see. I'm curious.
Like he numbers them as like 1, 2, and 3.
Sure.
He goes, okay, it's good with 1. It's like this.
Oh, but he's okay, so he's still okay. Yeah, he's doing the same thing I'm doing, just in a little bit of a different way. I don't find that particularly intuitive. Not that you're not allowed to do it, that you're obviously allowed to do it that way. Just I think what I'm doing is easier. But you can do it if it works better for you to do it his way, totally do it that way. Either way should be fine. So let me ask, for that one, did he do fx? Did he use fx and fy first? Or did you use fx and fy first? Okay, so, and that's pretty typical. It's usually very common practice just to grab the first two equations, set them equal to each other. So I said, let's use a different color. I said these two equal to each other. You get 3 over 2x equal to 1 over 2y. And then I would cross multiply and say 6y equals 2x. And if I'm solving for one in terms of the other, I can either isolate x and say 3y equals x, or I could isolate y and say y equals 1/3 x. We should really just pick one of them, but it's actually going to depend on what the next equation yields. So if I then use these two equations, set them equal to each other, 1 over 2y equals 1 over 3z, I can see that I'm either going to get z in terms of y or y in terms of z. And since I already have x in terms of y, I'm going to want z in terms of y, so that I can rewrite my constraint with just y's in it, excuse me. So cross multiplying here, or just flipping both sides over if you like. 3z equals 2y. And I said I wanted z in terms of y. So I'm going to get z equal to 2/3 y. So now I've got z in terms of y and x in terms of y. And I can replace x with 3y and z with 2/3 y. So then this constraint equation will be just in terms of y. And that's usually what ends up happening with these LaGrange multipliers. Not all the time, but most of the time. So our constraint, which you could write as f lambda if you felt the need to. I don't think we feel the need to. I'm going to write this constraint as x squared plus 2y squared plus 6z squared equal to 1. And I'm going to plug in for x, 3y, and for z, 2/3 y. I'm just going to do a little bit of algebra. So let's see. So 3y squared is going to be 9y squared plus 2y squared plus 6 times 2/3 squared is 4/9 y squared equal to 1. Simplifying a tiny bit, 6 and 9 reduces to 2 over 3. And I would multiply everything by 3. Right? I don't love fractions when I don't have to deal with them. So I'm just going to say, okay, multiply everything by 3. So 9 times 3 is 27 y squared. 3 times 2 is 6y squared. And 3 times 2 times 4 is going to be 3 times 8, which is 24 y squared equal to 3. Let's see. So this is gross, but fine. Yeah, really kind of gross, actually. So 24 plus 6 is 30, plus 27 is 57. So we've got 57 y squared equal to 3. So y squared is going to equal 3 over 57, which is 1 over 19. So y is going to be plus or minus the square root of 1 over 19. That turned out to be less nice than I was hoping for, but probably right, assuming I didn't do something stupid. No, that looks totally fine. I just often expect the numbers to be a little nicer on my work, but there's no really good reason for that. Okay, so then We're going to find the corresponding X and Y values, or sorry, Y and X and Z values. And we're going to get X is going to be 3 times Y. So really, X is just going to be plus or minus 3 square root of 1 over 19. I don't really need to write the ones. I guess I could write that as 3 over the square root of 19. And Z is going to be plus or minus 2/3 times the square root of 1 over 19. And here's what I should point out. Because of how X is in terms of Y and Z is in terms of Y, my 2 critical points have the same signs, meaning all the coordinates have the same signs, right? So if Y is positive, then X is positive and Z is positive. And if Y is negative, then X is negative and Z is negative. So my critical points are really, I'm going to write it as 3 over root 19, comma, 1 over root 19, comma, 2 over 3 root 19, and then the negatives, negative 3 over root 19, negative 1 over root 19, negative 2 over 3 root 19. And assuming we've done this correctly, which of these critical points can I plug into the function that I was trying to find the maximum or minimum value of? Which of these 2 critical points is going to give you the maximum value? The positive ones, because all my coefficients here are positive. So my maximum value should be 3 times 3 over root 19 plus 2 times 1 over root 19 plus 4 times 2 over 3 root 19, which is terrible, but fine. And then similarly, the minimum value is going to be the negative of that, which I would love to find room for. So the minimum value should end up being 3 times negative 3 over root 19 plus 2 times negative 1 over root 19 plus 4 times negative 2 over 3 root 19. So yeah, that's not my favorite problem ever, but totally fine. I would encourage you, for whatever version of this problem you have on your own, be sure to be extra careful checking to make sure you've got the right value of Y when you're solving this, because not that this is wrong necessarily, it just feels messy to me. And so I'm concerned I could have made an error somewhere, but the idea still holds, right? We found X in terms of Y, we found Z in terms of Y, we plug those in for X and Z respectively. We simplify this out, just double checking here, 9y squared, 2y squared, and 6 times 4 ninths is 24 ninths, which is 8/3. And then multiplied everything by 3, 27, 6, 8 times 3 is 24, 30, 57. Yep. Okay. That seems right as far as I can tell. So there you go. Okay. Let's start talking about double integrals. And here's what I would say. So we are going to use double integrals to talk about volume, but it's really kind of important to understand how we can use double integrals to find area first. So let's look at this first example here. Let's double integrals. So let's say we want to find the area in quadrant 1 that's between the 2 curves, y equal to 4x and y equal to x cubed. And I'll just draw it kind of okay-ish here. Here's y equal to 4x. Y equal to x cubed. I don't care what's going on in other quadrants, so I'm not going to try and draw it nicely there. Oh man, I could have drawn it better there. And let's see, these intersect. So if I set these equal to each other, 4x equal to x cubed. It's really not a good idea to divide by x. You could, and the x squared equal to 4, and see they intersect at 2 and -2 and also 0 because we divided by x. But the safer bet is to bring everything to one side and then factor. So you get x times 4 minus x squared equal to 0, or x times 2 minus x times 2 plus x equal to 0. So we get x equal to 0, which is the point 0, 0, which is, we know they intersect there. And we also get x equal to positive 2, which would be the point 2, comma 8. You would also get x equal to negative 2, but that's in a different quadrant, so we don't care. Okay. So normally, if you were using a single integral to find the area of this, the way you would usually do this is say, okay, well, the area is going to be, if I use a vertical cross section or vertical strip, the area is going to be the integral of, well, the height of that strip times the width of that strip. The height of that strip is the top minus the bottom. So 4x minus x cubed. And the width of that strip is dx. And we're going as far left as x equal to 0, and as far right as x equal to 2. What I want to point out, though, is we can actually write this as a double integral. So we can say that this is equal to, basically the idea is we can write this inner part here as an integral itself. That inner part is the integral from y equals 4x, sorry, bottom to top, not top to bottom, y equals x cubed to y equals 4x of 1 dy. Right? If you integrate 1 with respect to y, what do you get? Y. If you plug in 4x first and then subtract and plug in x cubed, you exactly get this. So this integral in red really does represent what I've underbraced in red there. And then we would do the integral of that from x equals 0 to x equals 2 dx. Now, normally, I don't say normally, most of the time people don't write the x equals and the y equals here. I like to because it reminds me of what's what. But most of the time people will probably write this as the integral from 0 to 2 of the integral from x cubed to 4x of 1 times dy times dx. The 1 people often omit. So if you see someone do the double integral of just dy dx, you should remind yourself that it's times of 1. So you're going to integrate a 1 first. Let's see, is there anything else I want to say about this? Yeah. One other thing I will say about this is when you're writing a double integral to describe a region between some functions, typically the inner limits of integration are going to be a function of one of the variables. If you have dy here first, it's going to be y equals some function of x. If you have dx here first, it's going to be x equals some function of y. And then your outer limits of integration, the ones that come last, because we would do that integral last, are always going to have to be constants. Something you'll see with practice, but I'm just warning you now. So let's see if we can do it the other way. Let's, instead of using vertical strips here, let's use horizontal strips. So now, to describe my rectangle width, I'm going to do the right function minus the left function. So my inner integral is going to be the left function on the bottom, the right function on the top, and that's going to be x equal to the left function, x equal to the right function. So we're going to have a dx, which I will totally admit sometimes feels counterintuitive to me. Because when I look at this kind of strip like this, I think of there being a dy, because that's like the width strip. But that's kind of the second step of this. And then the outer limits are going to be y equals how low we go to y equals how high we go. Now the top minus the bottom, which is how low the y's are. So in this particular case, it's going to be y is going to go as low as 0 and as high as 8. And the left function here, well, it was y equals 4x. If we solve for x, we're going to get y over 4 equal to x. That's my left function. And y equals x cubed, we solve for x, and we get x equal to the cube root of y, or y to the 1/3. So this double integral also describes all of this area here. both these double integrals, although they look a little bit different, describe the same area in the XY plane. And that's useful because sometimes we're going to want to be able to change the order of integration. Sometimes it's really going to make sense to integrate with respect to x first. Sometimes it's going to make more sense to integrate with respect to y first. Let's look. We got time. Yeah, we got time. I'm just convincing myself we have time. Sure. And I guess we could actually calculate one of these. I would probably do the first one. It looks a little bit easier for me to handle than the second one. So if we actually calculate this, that's going to be, so again, like you said, the integral of 1 with respect to y is going to be y. And then we're going to plug in the limits of integration. So then we're going to get the integral from 0 to 2 of 4x minus x cubed. And then we're going to anti-differentiate that with respect to x and get 4x squared over 2 minus x to the 4th over 4. And plug in the 0 and the 2 and get 4 times 4 over 2 minus 2 to the 4th over 4, which is 8 minus 4, which is 4. So that area is actually 4. So the reason we're talking about this is because eventually what we're going to do is we're going to imagine some surface that's above some region, and we're going to want to find the volume under that surface over some region like this. But let's look at one more example of this double integral stuff, and then we'll talk about doing a surface kind of thing, or a volume. So let's say we want to, we'll go, yeah, let's do the other one. Let's say we want to kind of go backwards and we want to sketch the region of integration, given by the following integral, double integral, 0 to 3, x squared to 9, dy dx. So I feel like I should let you guys try and do this, but time. We'll just talk about it. So here's what I'm thinking of, which I didn't write, but I like to think of. Really, this is the integral from, well, we're going y equals x squared to y equals 9. And then we're going x equals 0 to x equals 3. And like a lot of things in mathematics, you kind of want to work from the inside out. So I'm working with the inner integral first. I'm thinking, okay, I'm going from y equals x squared to y equals 9. So that's kind of giving me what I'm thinking of as my vertical strips, because I know that my y is bounded below by x squared and bounded above by y equals 9. And then the x limits of integration are telling me how far left and right we're going. So we're going to go as far left as 0 and as far right as x equal to 3. So we're getting this entire region between these two functions that's in the first quadrant. So that's exactly the sketch. I think there's other things I'm trying to say here. No, I don't think so. Do you have questions so far? I guess I should ask. Okay. So I'm going to make some blanket statements here. When it's dy dx, we are thinking vertical cross sections or vertical strips. Whereas when it's, so we could then switch it and use horizontal strips. And that's going to be when you have dx dy. But really, I mean, I wouldn't memorize this per se. I would just be like, well, I know if it's dy dx, the inner integral is y equals something, and the outer integral is x equals something, right? These go with this, and these go with this. And then if I'm trying to do horizontal strips, Again, the inner integral should always be the one that has the functions as limits, if there's going to be one. There is one type of region where all the limits of integration are just constant, which is nice, which we'll see in a second here. But for this one, using horizontal strips, well, I know I'm going from as far left as x equals 0 to as far right as, instead of y equals x squared, it's going to be x equal to, technically if I square root both sides, it'd be plus or minus the square root of y, but since we know that we're on the first quadrant here, it's going to be x equal to the positive square root of y. That's dx. And then the outer limits of integration is just going to be y equals how low? How low do we go? Here you go, like 0, as high as 9. And then we could put a 1 in there if we wanted to. So lots of ways of describing a region in 2 dimensions. So now, why do we do this? Well, so we can describe some volumes. Let me grab this example that I really wanted to do. Cool. So let's take a look at this example. And we'll try and draw. So we want to. So let's find the volume of the solid in the first octant. So remember, just like the first quadrant was where x and y are positive, the first octant was where x, y, and z are all positive. Bounded above by the surface, z equal to 6 minus y, and below by the square region, where x is between 0 and 2 and y is between 0 and 2. And let's draw it. So we'll try to draw it anyway as best we can here. So here's kind of my region in the XY plane. So that's kind of the square that our surface is going to be living above. And then our surface is the plane z equals 6 minus y. No, you're good, no worries. So I know that if z equals 6 minus y, I'm essentially just saying, well, if I set y equal to 0, z could be 6. And even though this isn't quite to scale, it's okay. So here's the point, 0, 0, 6. And then if y gets bigger, like if y is 2, that's 0, 2, 0, then z is going to be 4. So I'm going to go over here and maybe like that's that. So it's going to look kind of like that. I'll have the same kind of thing happening over here. And then I messed up. I was doing so well with my drawing and I blew it. Wish I had white out. Do I have white out here? It's so disappointing. It was going to be, man. Okay. It was supposed to be parallel to that line there. So disappointed. You don't even know. It's supposed to be more like this. Sorry, I just ignored that stupid line there. And so basically the idea is that this is our solid. And so the idea is that we're kind of breaking up the region in the XY plane into all these little squares, which are a little dx and a little dy. And then we're kind of seeing, okay, well, if I look at the height of this square, right, I'm going to find the volume of this little box. I'm going to add up all the volumes of the boxes. So I want to point out that the kind of volume of my little box there is the height times a small change in X and a small change in Y. And then we're going to add up all the boxes. So the total volume is going to be the sum of all the volumes of the boxes. Which your professor, I think, talked about how it was like f of xy times dxdy. So the idea is basically we're just trying to add up over this entire region. And the way we do that is we say, well, it's going to be, we're going to integrate over that region, which is why we spent some time, 2 examples, talking about how to describe the area of the region with the integral. Because what we have to do is say, oh, this region here, that's just going to be x going from 0 to 2, y going from 0 to 2. And then since I've done x, then y, I should do dy, then dx. Not that it would particularly matter here, since literally x and y have the same absolute integration. And then my function would be z equal to 6 minus y. That's my function of x and y. There's no x isn't specifically this time, but that's what we've got. So that will give us the volume of this shape. Well, we can do that. That's going to be the integral from 0 to 2. If I integrate 6 minus y with respect to y, I'm going to get 6y minus y squared over 2. Oh, from y equals 0 to y equals 2. Then we plug in y equals 2. So I get 12 minus 4 over 2. And then I plug in y equals 0, which gives me 0 minus 0. So I'm not going to write it down. And then we do the same thing. I'm going to integrate this. I'm going to integrate 10 and get 10x from 0 to 2. And then I'm going to plug in 2 and get 20 minus 0, which is 20. That's how we find the volume of a shape like this. Now, the thing is, we're not always going to be integrating over some nice square like this. So let's look at, let's talk through an example that I have over. No, fine. Let's do one more real quick, like. So let's say we want to find the volume of the solid in the first octant bounded by x plus y plus z equal to 1. Here's what it looks like. It's got x, y, and z intercepts that are all 1. So intercept there, intercept there, intercept there. You can probably draw this one without screwing it up. And so here's our region that we're integrating over. And we're going to be taking little squares and then seeing what I drew the square in like the worst place I could have drawn it. We're taking little squares like that and then adding up the volume of that little box. So we have to do the double integral over the region, which we typically call R. Some people, you could write region if you wanted to, of your function of x and y dA. People write dA when they want to say like we're integrating over this area, but we're not sure if we're doing dx dy or dy dx yet. So then typically what we want to do is we want to take that region and draw it in the xy plane so that we know what it looks like. So there's my same region. And I'm going to describe this the way we did for the previous 2 problems. We're like, oh, I need to describe this. I can either use vertical or horizontal cross sections. Let's go ahead and use vertical. So I'm thinking, okay, my double integral is going to be going from y equals 0 to y equals 1 minus x. And then x is going to go from 0 to 1. And so it's going to be dy dx. And then the function that we're integrating, we have to solve for z as a function of x and y. So our function of x and y, if we have x plus y plus z equals 1, we get z equal to 1 minus x minus y. And there's your height as a function of x and y. Whoops, not z. Good God, James. So 1 minus x minus y. And then you would do the same sort of thing. So you would integrate this with respect to y first. So check this out. This is where things are. Let me just do this one thing. We integrate this with respect to y. The integral of 1 is y. The integral of x is x times y. I should really say antiderivative. The antiderivative of 1 is y. The antiderivative of x is x times y. And then antiderivative of y is y squared over 2. From y equals 0 to y equals 1 minus x. And then we have to plug in the 1 minus x and the 0 for just the y. So we're going to get 1 minus x times 1 minus x minus 1 minus x squared over 2 minus 0 minus 0 minus 0 is 0. And then you would simplify this and then anti-differentiate and then plug in 1 and 0. Which is not too terrible, but it's a little not fun, right? That doesn't look nice, but it's totally fine. If we simplify this, we get 1 minus x plus x squared, and then minus 1 minus 2x plus x squared all over 2, which I'm just going to tell you, you'll get 1/6. You should do it on your own. It's fine. So that's kind of the big picture is why we talked about the areas so that we can write the region that we're integrating over as the double integral of whatever to give us that area, and then the thing we're actually integrating is the height or the surface that we are underneath. That's it. We'll do more of these on Friday. Yeah. So what I'll say here is usually the integration part is not too terrible, give or take. Usually it's the figuring out what the limits of integration are to describe the region in the XY plane that is the typically more challenging part of these problems. I know it's kind of hard to care about this quite yet because I know you don't have any assignment on it yet, but just start thinking about it. And I can give you extra problems if you want.